Hey everybody, a really exciting lesson going on today, and I have a lot of examples, so let's get in it. Whoop. Today we are going to get into graphing polynomial graphs. I like this lesson, everybody. Before we get into the graphs, whenever you graph these problems, there's three things you want to think about. First thing you're going to think about is the zero's location. X minus 3 has a 0 at 3. X plus 4 quantity cubed has a 0 at negative 4. Stuff like that. Next thing you want to think about is the end behavior of the graph. Is it up, up, down, down, or up, down? Then you get into the business of graphing, and the only new stuff is the zero type. There's a single zero where the graph passes straight through the x-intercept. There is an even zero, like x squared, x to the 4, x to the 6. In that case, the graph bounces off the x-intercept. And then there's an odd one, and I don't mean single, I mean odd as in like x to the 3, x to the 5, x to the 7, etc. An odd one does this like slow down thing and then speed up thing at the x-intercept. And we're going to talk about this in class on Friday to explain why single, why even, and why odd does this. But for right now, if you're watching this before the lesson, you're just going to have to believe Elliot. All right, let's get into the business. Graph. I don't need a y-axis on these graphs. I only need an x-axis, just for your own personal work. As I mentioned before, the first thing I want to think about is the zero's location. Because of this x plus 3, I know that I have a 0 at negative 3. And because the x minus 4 squared, I know that I'm also going to have a 0 at 4. Next thing I think about, end behavior. End behavior. In this case, this works out to be an x squared. This works out to be an x. X times x squared is x cubed. So it's positive x to the odd. So because it's positive x to the odd, that is down, up. And then finally, the type of 0, because negative 3 is just to that first power. Negative 3 is a single 0, and the 4, because that x minus 4 is being squared, that's a double 0, so I would want to think of that as being even. Now we get into the graphing. Down. End behavior. So you start graphing with the end behavior. It's going to be down, so I know it's going to head down like this, and it's going to head up towards negative 3. Negative 3 is a single 0, so it passes straight through the line. Then somewhere in between negative 3 and 4, this graph is going to magically turn around. It's not magic, and you'll learn in 2 years in calculus how to find that exact point. But then it's going to head down towards 4. And at 4, that positive 4 was an even 0, and even zeros bounce off of the x-axis. So at 4, it's going to bounce off, and then it's done hitting the 0, so it's not going to turn around again. And at that point, it should be heading up, and it says that our end behavior here is up. So this graph would end up pointing up like this. So this graph ends up looking pretty much like that. Pretty neat, huh? Well, I hope you find it neat. I have 6 of these examples total. Each one will last probably 2 minutes. Example number 2. Number 2 is j of x equals negative 2 times x plus 3 to the 4th power and x minus 5 to the 6th power. All right, so going through the list. 0 locations. Because of the x plus 3 here, I have a 0 at negative 3. And because of the negative x minus 5, I have another one at 5. End behavior. I have negative 2 times an x to the 4 times an x to the 6. So that's negative 2 x to the 10. Negative x to the even, so that means that this end behavior is down, down. Meaning, it's going to start down here, the arrow's here, and it's heading up towards negative 3. Now we start thinking types of zeros. At negative 3, it's to the 4th power, that's even, which means the graph is going to bounce off the x-axis at negative 3. Somewhere in between negative 3 and 5, the graph is going to magically turn around and start heading back towards the x-axis at 5. At 5, it's to the 6th power, that's even, which means it'll bounce off the graph again and be heading down at that point. And if I look back at my end behavior, it does say down, down, so it's pointing down at the end just like it's supposed to. And that, everybody, was example number 2. If you have any questions along the way, you should stop the video and ask Elliot. He'll answer for them as best you can. Example 3. M of x equals x times x plus 1 quantity cubed and x minus 5, all that to the 4th power. All right, now, people frequently make mistakes on this problem because of this x here. That means that there is an x-intercept at 0. X is just like saying x minus 0. So we have an x-intercept at 0. Because of this x plus 1, I know I have an x-intercept at negative 1. And because of x minus 5, I know I have an x-intercept at 5. Just to demonstrate how, I don't want to say inaccurate I'm making these graphs, this distance from 0 to negative 1 would definitely be a lot shorter than the distance from 0 to 5, but I have them pretty evenly paced out almost. That's okay as far as I'm concerned because we're putting these numbers on the x-axis. End behavior. There's no leading coefficient here, but it's x times an x cubed times an x to the 4. That's an x to the 8. Positive x to the even. So we're talking up and up. So over here, the graph is pointing up. It approaches negative 1. Negative 1 is to the 3rd power, meaning it's going to do this speed up, slow down thing. So it's going to look like this on this end, and on this end it's going to look like that. So it's not passing straight through, slowing down, passing through, and then speeding up again. Somewhere between negative 1 and 0, the graph's going to magically turn around. It's not magic, it's math, but it feels magical. At 0, this is an x to the 1, so it's going to pass straight through at 0, not doing the slow down, speed up thing like we did with the 3rd power. Then it's going to turn around somewhere in between 0 and 5 and head down towards this new x-intercept. This x minus 5 is to the 4th power, meaning it is going to bounce off the graph, head on up, and that's it. What a nice looking graph. Elliot Likey. All right. Example 4. I have a total, like I said, I have a total of 6 of these. I really like these problems. I find them quite enjoyable. Example 4. K of x equals negative 4x squared, x minus 3 to the 4, and x plus 5 to the 3rd. So x-intercepts, because of the x squared, it's like x minus 0 squared. So there's an x-intercept at 0, there's an x-intercept at 3, and there's an x-intercept at negative 5. End behavior. I have negative 4 times x squared times x to the 4 times x to the 3. This ends up being negative 4x to the 2 plus 4 plus 3 is 9, so negative 4x to the 9. That's so negative x to the odd. X to the odd is usually down, up, so this one means it would be up, down. That's the math that I run through in my head. I just have x to the even and x to the odd memorized, and then if it's negative, I think about the reflection of it. So up, down. So as it approaches -5, it's going to approach from the upward direction. At -5, it's a triple. That's an odd. That means it's going to do the slow down, pass through the x-intercept, and then take off again. Somewhere between -5 and 0, it's going to turn around. 0 is squared. That's even. That means it's going to bounce off. And then it's going to turn around again. And then somewhere between 0 and 3, it's going to turn around again. And x minus 3 is to the 4th power. So it's going to bounce off and head on down. And at that point, I'm out of zeros. So it should be pointing down. And if I look at my end behavior, it does say down. So the end behavior on the end, it's always kind of like an added step of redundancy. My graph was already pointing down, so it makes sense that that would say down at the end. All right. Example number 5. This is getting more and more fun. Wait till you get to example 6. Or should we get to, no, let's do this one too. H of x equals x minus 2 quantity cubed, x plus 1 quantity squared, and simply x plus 5. All right, I'm gonna go quickly through this one. I'm really excited to get to example 6. I have a 0 at -5, a 0 at -1, and a 0 at +2. This is 3 plus 2 plus 1, so that's positive x to the 6th. So this is positive x to the even, meaning up and up for the end behavior. So it's going to be pointing up here, heading towards -5. -5 is a single, so it's actually going to pass straight through at -5. That's not a good graph. Elliot's going to have to start this over. -5, -1, 2. It's the downside of using pen, everybody. I don't recommend it for everybody. Graph passes straight through at -5. -1 is to the 2nd power, so it bounces off. And +2 is to the 3rd power. Oh, so the 3rd power means it's going to do this slow down, speed up thing. So it's going to do something like that. All right, single, double, triple. This is a very typical quiz or test question because it contains all 3 types of zeros. Now, number 6, this is the humdinger, and we'll say this happened at 12:45, so that people can just jump to the end if they want to. Number 6 looks like this: g of x equals 3x times x minus 5 times x plus 3 quantity squared times x minus 4 to the 3rd power times x minus 2 to the 4th power and x plus 1 to the 5th power. Even though this problem is big and ugly looking, we treat it the same way we treat all these other problems, and it'll work out the exact same way. Zeros. You might want to work your way from left to right. It looks like I have one here at -3, then one at -1, then one here at 0, then one at 2, 4, and 5. 2, 4, and 5. All right. End behavior. I have a positive 3x to the 1. This is another x to the 1. This is an x squared. This is an x to the 3rd, an x to the 4, and an x to the 5. So that's 9, 10, 16. 5 plus 4 plus 3 plus 2. So far that's 13. Wait, I said that wrong. That's 14. 9 plus 5 is 14. 15, 16. So this is positive x to the 16. Positive 6 to the even. Positive 6 to the even means up and up. So as I approach -3, I'm approaching -3 from the upwards direction, and -3 is a squared, meaning it's going to do some kind of bounce off thing. It's coming from the up, -3, it bounces off. then it's going to turn around, and at -1 it's to the 5th power. So -1 is going to do the slow down, speed up thing. So it's going to turn around, hit the graph, do the triple, then it's going to turn around again at 0. That's a single 0, so it's going to pass straight through. At 2 is to the 4th power, so that's even. So I do the bounce off the x-axis thing. At +4 is a triple, so I treat that one like it's an odd. So it does the slow down, speed up thing. And then finally, number 5, 5 is a single. So at the single, it's going to pass straight through. Wow. This problem had a lot of pieces to it. And I've mentioned this before. You can always use Desmos to check your answer. So here's what my graph looks like. And then here's a Desmos graph on it. So let's see. It's kind of tough to see here at -3, but if you can see it, it did actually, you kind of have two lines here. So it came from up here. Oh wait, I gotta work like this so you can see it. Yeah, there you go. So this is how it works? Yeah, okay. So the graph it came up, it bounced off at -3, it came back around at -1. There was this triple, at 0 a single, at 2 a double, at 3 a triple or an odd, and then at 5 it passed straight through and it headed on up. So it's all there. Awesome. So that's what the graph looked like. I have one more quick problem to show you. This is a write the equation problem. Get out of there, Desmos. And this I need to write an equation. And they just give us some more information now. So I have roots, or zeros. I have a root at x equals 2, but they also let me know that it's a single 0. I have one at -4. They let me know that that one is a double. And I have one at 5, and they let me know that that one is a triple. And then it passes through the point 0, -36. So this problem works just like these problems worked when we're doing this for quadratics or for cubics. You start off with y equals a times, because there's a root at 2, it's x minus 2. It's a single, so it's to the 1st power. There's one at -4, so it's x plus 4. It's a double, so I'd put it to the 2nd power. And the 5, so I'd have x minus 5. But that's a triple, so it's to the 3rd power. Now the point 0, -36 comes into the equation. So it becomes -36 equals a times 0 minus 2 to the 1st, 0 plus 4 to the 2nd, and 0 minus 5 to the 3rd. Be careful with your math. This is going to get complicated. 0 minus 2 is -2. -2 to the 1st power is just -2. 0 plus 4 is 4. 4 squared is 16. 0 minus 5 is -5. -5 cubed is -125. I got to use a calculator here. 2 times 16 times 125 is, whoa, 4,000. And it's positive 4,000. So -36 equals 4,000a, which means a would equal -36 over 4,000. Let's see, both of these numbers are divisible by 4, so I could get -9 over 1,000. That'll work. So my answer is y equals -9 over 1,000 times x minus 2 to the 1. I don't even need to write the 1. X plus 4 to the 2. You do need to write the 2 though. And x minus 5 to the 3. All right. This lesson was a little bit long, everybody. My apologies. Have yourselves a beautiful day. Talk to you later. Bye-bye.